So now it's recording, and well, let us see what's going on with this interesting chapter 4 that talks about numbers that we used to deal with in everyday's life, but it talks about a little bit different ways to present numbers. So let's say here they are looking at 3 ways to write exactly the same number 9. So number 9 that we used to, well, just write as 9 could be also treated as a Roman numeral, to put this in the following format with that like X and a bar in front of it. Or I guess intuitive way to produce notation for same exact number 9 could be using so-called tally method. Well, probably the fastest way is to use our favorite notation, with just the so-called Hindu Arabic numerals. That's what we used to have, because with tallies, if you try to put number 900, that'll take you a while, right? So you need to basically put 900 of those little tallies, and that's, well, kind of waste of time. But depends on the purpose. So textbook is not available for free online, and I told people that what I can do is just record my lectures, and right now I hope you can see the textbook in front of you, the first page of chapter 4 opened, and I guess that's the only thing I can do here, because I was trying to find a textbook for free for you online and I couldn't. So I guess the best we can do is just have this in recordings of lectures, and eventually I'm going to move to the end of this first section of chapter 4, and you will be able to see the homework problems as well. So I guess that's the way to go here. Or else, yeah, if you want, you can always purchase the textbook at our bookstore. They sell this online links as well as hard copies, so it's your decision. But I would say you don't really have to buy it, because if you are here, or if you watch the recording of lectures that I will be emailing to everyone a little later today, I'm recording today's lecture, so you will be able to see the textbook in that recording as well, because I just always share my screen. So they, let's go back to this story. So they also produce so-called exponential notation that describes numbers. And you're probably familiar with the way to write numbers using powers, like b raised to the power of n means that you have n b's multiplied together. So using this so-called notation will be the key idea in producing digits for numbers. So what they're talking about here on the next page is numbers such as, for example, 1, 2, 3, 4, and they say that 1 shows the, so I'm going to put it like that, 1 plus 2 plus 3 and plus 4. So number 1, 2, 3, 4, which actually supposed to be called 1234, is nothing but a 1 multiplied by 10 to the power of 3. Then I have 2 multiplied by 10 squared, 3 multiplied by 10 raised to the power of 1, and 4 multiplied by 10 raised to the power of 0. So it turns out that every number that we have in so-called base 10 notation, and that's the way we treat our numbers all the time, in base 10, I have to write this with powers of 10. In other words, people say this is going to be 1,000, right? And then 2 hundreds, and then 3 tens, and 4 ones. And that's actually basis for describing all the numbers in a familiar way that we are used to in the real life situations. Let me check the email. I think could be someone is trying to come over to our virtual class by sending me email. So let me real quick see what is going on here. Actually, no, I don't think so. Okay, so let me share back. Let me see. Zoom is not working. Let me write this again. Use MDC. Yeah, usually it's the same exact issue. People like to try to log into the Zoom not using our email, but I guess eventually everyone will get used to this. So anyways, let me go back to the textbook and well, just refresh your memories on how the numbers the ideas behind writing down the numbers, like 663 here, they say it's 6 hundreds and 6 tens and 3 ones. So it's not really surprising. Well, the reason we do this is because it turns out there are some other so-called bases in writing numbers. What does that mean? Well, for example, there is a so-called Babylonian numeric system that our scientists decided was used back in the years in so-called Babylonian ages, when it, who knows how many years ago, they say 1400 years before our centuries. So that's a while ago, about 3,000 years or 4,000 or so. So anyways, how did they write numbers? How they used to write numbers? For example, how did they write number 4,202? Well, it turns out instead of using base 10, because number 4,000 is actually 4 times 1,000, right? Plus 2 times 100, because it's 200. Then there is no tens, so I put 0 times 10, and then 2 ones. They will write quite differently in that system. So what they actually do is they put base 60 numbers. So what they, instead of using powers of 10, they used powers of 60. Look at this. 60 squared is multiplied by 1, so they just put 1 here. Then they had 10 of 60 to the power of 1, so somehow they have to have the symbol for 10. So that's our first digit. Then here's the second digit, which is 10. The next digit is going to be 60 to the power of 0, which is 1. So what they do is they put 1, then they put 10, and then they put 1, which is quite unusual, one can say, right? So what they do is instead of 1, they used like a check mark, and instead of 10, they used this type of a symbol. So instead of 1, they had check mark, and instead of 10, they used this symbol, and then they used that. And this number is actually same as 4,202. You say, wow, that's just unbelievable. How would they guess that this was 4,202? Well, it's so-called base 60 for the numbers. Let's see, that's just unbelievable. How were they able to figure that out? Well, I guess that's what archaeologists are facing in their work, and that's quite an amazing thing, I guess. So let's take a look at another example, example 3, that actually continues this story on the page next to it. So in example 3, they actually consider more numbers in this unusual writing way. So what they do is they put here this bunch of check marks and other little symbols in here. So here's the little number they have for the 60 squared, and then for first power of 60, and then for ones. So the actual number they have in here looks like they have is this 2, and then next 2, and then next 4 little digits. So what did they stay for? Well, it looks like this one stands for 1, and then another 1. So that's basically 1 plus 1, which is 2. So in our so-called Hindu Arabic way to write down the numbers, we just put 2 for that digit. Now, the next one looks like we have that wiggle, that symbol actually, and then next to it, there is a check mark. So they say that this symbol stands for 10, and the check is another 1. So this is actually 11. Let me get that. So 11. And finally, the last one has 4 little symbols. So what kind of number is that? Well, it turns out that we have a couple of 10s. These 2 symbols, they stand for a couple of 10s. Let me underline so we can better see what's going on. So these 2 stand for a couple of 10s. And here they are. And then there is a couple of 1s. So the other 2 is a couple of 1s. So we have 20 and another 2. So this will be 22. And then when you take each of this and multiply by powers of 60, so we're gonna deal with the 60 to the power of 0. That's our last digit. This is gonna be 60 to the first power, right? 60 raised to the power of 1. And the first will be dealing with the next power of 60, which is 60 squared. And when you add them all together, you will see what Hindu Arabic representation of numbers. So if you multiply 2 by 3600, and then 11 by 60, and then 22 by 1, and that's exactly what they did here. 11 60s and 22 1s, and put them all together, they get actually 7,800 82. You say, Alex, why wouldn't they just use this normal way to write down numbers? Well, back in those ages, they say there was no Hindu Arabic way to describe numbers. And that's exactly what happened. Well, I guess they had some other ways to describe numbers until eventually this base 10 system or Hindu Arabic system was designed. So looking at this example, I think one should really appreciate to what is going on right now, because it's quite challenging, right, to be able to write those numbers in other systems of enumeration. So this first section of chapter 4 introduces us with various historical ways to write the numbers. And next system is Mayan, that I guess archaeologists discovered that system has actually base 20 to write down numbers. So you can see that instead of our favorite digits 1, 2, 3, 4, 5, 6, 7, etc., all the way to 9. So there are actually 10 digits that we're using to produce numbers. Please notice that first digit is 0 as well, right? Because then when you get the next, it's going to be 10. Well, in Mayan numeration system, they actually had 20 different digits. Look at them. So for 0, they use something kind of similar to zeros, like circular thing, right? Then for 1, well, we had just 1 dot. For 2, there are 2 dots. And then once you hit 5, you get a bar, right? And then when you have 6 and 7 and so forth, you start adding dots above that bar. And then with next digit 10, actually next number 10, they had their own digit-like expression, this couple of bars, and so forth. So technically, they had this 20 different digits produced, and the base for the system was 20. Isn't that amazing? So here's a good example that people might encounter if they start to do archaeology here, and I guess South America. And this Mayan numeration system is quite an interesting example. So let us take a look at example 4. So how you can write various Mayan numerals and what they actually stand for. Let me clean a little bit of this mess I produced. So I'm going to look at example 4, part A, well, just to read along with the statements that textbook has. So our goal today is just to start to realize that numbers that we used to write just quite automatically, well, could be treated a little bit differently. So for example, what this stands in terms of so-called Hindu Arabic or standard numeration system that we used to in the everyday life. And it turns out the number that they have here in example part A is 1952. I say, how do you know that? Well, it turns out that we're dealing here with base 20. So first digit, the one on the top, will deal with 20 raised to the power of 2. So base 20 means we have various powers of 20. So the next digit is dealing with 20 raised to the power of 1, just 20. 20 raised to the power of 1. The next digit deals with, so it looks like they have 14 for the first. The next is going to be a 0 for, actually not 0, but there's a 18. The next will be just the 20, and the last is going to be a number of ones. Well, it looks like here we have various ways to present these little digits according to the previous page. So if you look at the previous page and see what this all means, so there's 2 bars and there are 1, 2, 3, 4 on the top will stand for 5 and another 5. So it's just like 5 here, 5 here, and 4. So if you put them all together, 2 5s and 4, you get 14. So this first digit is 14. And that's a second power of 20. And the next digit is 0. Remember, this way is to write 0. So next digit is 5 and a couple of dots, so that's 7. So that's what they have here. And finally, for the last, we have 2 5s, which is 10, and a 2, which is 12. And then we have these 12 ones, 7 20s, and then we have the next digit, which is staying for number of 360s, and then next digit that tells us how many 20 squared will be present, and that's going to be 7,200. Somehow they put this together. So I would say that's not very convenient, right? I guess the idea that people get when they look at these examples, they wonder, well, why do we do that? Because it's not really probably the best way to present numbers. Well, main reason why is because our computers, you all know that computer processor has its own language, and it's actually produced in a base 2. So we don't really use Mayan numerals in a everyday's life, but what we do encounter is numbers, actually computer programmers encounter numbers in the base 2. And that's the, well, I guess, quite an interesting discovery that some people can make. And I guess that's what we should realize. So I definitely not gonna get very deeply into the Mayan system. My goal is just to get used to that, will just give you an idea that there are some other ways to present numbers exist, but just to look at the first portion of this section. So I'm not really expecting you to get into this group of exercises. That's okay, you can simply skip those. But just to recall how we actually write numbers using our standard way to write them. And the standard way is just the favorite Hindu Arabic system. So I'm gonna take a look at exercise like 23. That says we're dealing with 7 10s and 3 1s. So the number is actually 73, right? So it's pretty straightforward. So express the number in Hindu Arabic numerals. So that's 73 that has 7 10s, 7 times 10 and 3 1s. So that's the idea, to write down the numbers. So if I try exercise 26, analogously, I'm going to put just the first digits that we see here, such as 7, 5, and 3. And when I put them together, I produce the number 753. So I guess the system, so-called base 10, because we deal with powers of 10, is very convenient one to operate with. And of course, the digits, such as from 0 through 9, are the ones that we utilize on daily basis, and we'll actually utilize those digits as well in the next sections of this chapter. So I don't expect you to memorize that, let's say in Mayan system, this number that looks like what, couple of bars here, right? And 4 little dots. So there's like each dot is for 1, and then if we have a couple of bars, so that'll be 5 and another 5, so it'll be like a 10 and 4, so it's actually 14. But I don't think we need to memorize all that. So if you're interested, you can definitely take a look at more of these exercises, but I would say you don't have to worry about them. So how about if I try number 32? Well, looks like it's another similar type of exercise. So we need to see what powers of 10 we have in here. Maybe I can make this look a little bit bigger. So let me try to zoom in so we can better see what's going on. So you can see that we have not 354. So let me do exercise 32 here. So it's not really 354 because there are some powers of 10 skipped here. So the actual problem 32, if I want to be a little bit more careful, then I should write the following way, this number. I have 4 times 1. Then I don't have any other digits with powers of 10. So I have 0 tens here, 0 hundreds, right? Or 10 squared. And 0 times 10 to the power of 3, 0 thousands. But we have now 4 10,000s. You see how this number should be actually treated? So I don't really skip any of these powers of 10. And this way I will be able to see the digits that actually supposed to be present in this number. So I have no 10 to the power of 5, no 10 to the power of 6, no 10 to the power of 7, 0 of them. But there is a 10 to the power of 8, right? And I have 3 of those. So now I can easier write down the actual number we have in exercise 32. So I put 3, that's the first digit. Let me underline what I'm gonna write now. So there's 3 here, 0, 0. So they hold in place for those digits that were skipped. So I just have to put this together, right? So the actual number they have here is 3 and 3 zeros that follow. Then there is a 4, right? And then more zeros. And finally 1. So this number is actually something like that. It's 300,040,001. So that's our number. And again, the reason it looks so lengthy is because they decided not to write those zeros, because when you multiply by 0, this will just disappear. So they decided what for. So it's important to realize how we actually produce our numbers. Well, how about the previous? Excuse me. Let me look at the previous group of exercises. So now we can actually take our numbers and expand them, like 36, that we can treat as 3 tens and 6 ones, right? So that's what they expect us to do with this group of problems, right? Them with various powers of 10. So if I try, for example, exercise 17, what I can do is treat it as a 3 times 10 raised to the power of 4. And then there is no, or 0, 10 cubes, right? Next digit is 0. The next is 7, so it's 7 10 squared. And finally, 0. Actually, I wasn't careful. It should be 10 to the power of 0 in here, right? So this should be power of 1, this power of 2. See, that's why it's more convenient to always write this starting at the end, because this way you're not gonna get extra digit or something. So always 0 power and then first power and then second power and then third power of 10 and so forth. So what we just did, we produced the expanded form where one can say it's 3,000, and that's how we actually pronounce our numbers, and 0, 100, 0 times 100, and then 7 tens, 7 times 10, and finally no ones, or 0 times. So I guess the step here was a preparational, we wrote with powers of 10, actually gives us a better feeling how we get this number of 1,000, 100, tens, and then ones. And it's always like that. And it turns out they trying to give you an idea of analogy with other numerational systems in here. And that's what is happening. But as I said, I'm not going to really get deeply into this notations, because unless you're archaeology major, I don't think you will encounter these symbols ever in real life. But in the next sections, we'll actually see how this could be utilized and just doing some exercises. And I think it's interesting. So the first group of exercises is something that you're probably very familiar with. Let's say if I try exercise number 5, that deals with number 3 multiplied with itself 4 times. Well, that's probably your favorite, right? Just multiply a couple of 3s, you get 9, and then multiply another couple of 3s, you get another 9. So 9 times 9 will be 81. Well, just powers, so I'm sure you know how to do that, right? Well, let me take a sneak peek into the next page so I can just take a look at what's going on here. And you can see there are practice plus exercises that I told you not to worry about for the homework. So we just here in this particular section for problems that appear on first page, so exercises up to number 32. So I did some of those today. Let me clean this mess once again. So I'd like to also slightly touch section 4.2 just to give you a flavor of what we'll be doing in chapter 4. So I'm gonna just try to take a look at base 2 numbers. And today I just want to not to hurry, but little by little start to get used to a different way to present numbers. And a different way is right here. So how we can write the numbers we used to deal with in a base 2. So we already noticed that's what people that major in computer science are actually doing. So it turns out that in the base 2, we have only 2 digits, 0 and 1. So for base 2. So if you look closer at this little table here, you will see that all of the numbers, let's say number 16, for example, are produced from only ones or zeros. Interesting, right? So let's say if I am looking at number 16 and wonder why they write it as a 10,000, well, that's actually not a 10,000. They write it with powers of 2. So if I look at those digits, such as 4 zeros and a 1, then what I have to realize is that all of them are multiplied by powers of 2, such as a 0 power of 2. And this one is multiplied by the first power of 2. And that digit is multiplied by second power of 2. You see that? And then it's multiplied by 2 cubed. And finally, by 2 to the power of 4. So we do increase the powers of 2. And I guess that's the idea of producing the numbers. So I actually multiply this by 16. This one by 2 cubed, which is 8, right? And 2 to the second, which is 4. And then we have 2 to the first, which is just a 2. And then 2 to the power of 0, that's 1. And notice when you're adding 116 with 0 times 8, which is 0, with another 0 times 4, which is also 0, and so forth, another 0 and another 0, you do have a 16. Isn't that just amazing? You see, well, this way to write 16 is not convenient to put 1 and a bunch of zeros. Yes, it is not, but I guess that's how the computer processor is made. And I guess one needs to be aware of it, because when you start doing programming of computer, well, the processor will understand 1 and a bunch of zeros is 16. And you cannot put 1 and 6 in it. You just put 1 and these zeros. That's how it's designed. So yes, there is an application in real life of all those processes. And as I said, today I just want to start to get used to this unusual way to write the numbers. And next times we'll, I hope, get better and better with this. So let me try another one, like 7. So it turns out that 7, you can write with a bunch of ones, with 3 digits 1. And again, the last will be multiplied by 0 power of 10. 1 before is multiplied by the first power of 10. And the, oh, sorry, not powers of 10, powers of 2. I got carried away. Powers of 2, because that's base 2 numbers. Fix this real quick. So put powers of 2 here. So it's 2 to the power of 0, 2 to the first, and 2 to the second. And then you can see that you're actually multiplying 1 by 4, right? And then 1 by 2, and finally 1 by 1. And when you add 4 with 2 is 1, then yes, you see that this is equal to 7 indeed. So 7 is splitted with powers of 2. Interesting. How about if I try to make up, well, let me look at this example. Please notice that first of all, they write word 2 here on the bottom, which tells us that we don't really have 1001 in here. No, it's not 1000. It's 1 multiplied by various powers of 2, such as 2 to the third, and next is 2 squared, and next is to the power of 1, and finally 0 power of 2, which is ones. So we take all those digits, and that'd be 1, 0, 0, 1. So first is 1, then we have 0, then we have another 0, and then 1, and they all multiplied by powers of 2. So please notice it's far from obvious to understand what kind of number we're actually dealing with in here, right? But once you produce those powers of 2, so you see this is 8 to cube, right? This is 4, so it's down below here. And then 2 the first is 2, and finally once, then you multiply these by whatever digits you were given. So you have 8 with nothing, and with another 1. So 8 and 1 is 9. Isn't that just amazing? Let me produce number on my own. Let me just produce 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Alex, maybe enough. Well, I think it's plain indeed. So how can I write this number? I just made up a little example in familiar, favorite Roman numerals, not Roman, Hindu Arabic digits. Well, looks like these digits of number will be multiplied by various powers of 2. So let me rewrite all that, but give it a little bit of a room so I can squeeze in powers of 2. So 1, 0, another 1, 0. So how many? 2, 4, 6, 8, 2, 4, 6, 8. So another 1, another 0. Okay. So the number we have here in the base 2, I just copy it, and I'll be multiplying by powers of 2. So I start with 0 power at the end, then with a first power. So this is a standard way that ones that should start to get used to a little by little. So next will be 2 cube, right? And then we have 2 to the power of 4. So I can say the good thing in these calculations will be the fact that all those zeros we just disregard, right? But just care for non-zero digits. So next is 2 to the power of 6. And then we have 2 to the power of 7, just a couple of more. See, they're lengthy, those numbers. 2 to the power of 8, and finally 2 to the power of 9. So please notice it's not very convenient to deal with very lengthy numbers. So now I need to decide what I actually care about in here, because as we already noticed, these zeros times anything will simply disappear, give us 0, so I wouldn't really care for this. So what I do care is 2, which is first non-zero, plus next will be 2 cubed, which is 8, right? Okay, so what's next? 2 to the power of 5, which is 32. Right. Next will be 2 to the power of 7. So what I do is I multiply it by 2 and by another 2, so it's multiplying by 4. So if you multiply 4 by 32, what do you get? 4 times 30 is 120, and times 2 is 128, right? So our 2 to the power of 7. And finally, what be the next to the number next to it? Well, looks like you can probably use a calculator for that if you want. In fact, why don't I use a calculator? I think it'd be a better idea than just do it in your head. So to get a calculator, what I can do is just open the Google and type scientific calculator. Just start typing and it comes out. And I will use so-called Desmos. I think it's most convenient calculator that we have here. Let me clear this mess a little bit. So what I was going to do is multiply 2 with itself 9 times, or just to deal with 2 raised to the power of 9, right? And that's 512. So it looks like the number we had here was 512. So now I need to add 512 with 128, with 32, with 8, and with a 2. And of course, I'd rather use calculator to do this correctly. So easy to get mixed up. So why don't I just add 512 with 128, and I'll produce the actual number for what I just wrote in the base 2 numerals. So it's 682. So this is 682. How about that? So instead of writing this bunch of ones and zeros that I just created, well, we'd rather just put 682, and that'd be it. Interesting. So they have a little table here for us. So they produced various numbers of base 2, and you can actually produce this type of table on your own. So you just need to see how those digits vary. So if you have 1 digit only, it could be 0 or 1. Look at the first. You could either have a 0 or 1, and that's it. So there are 2 choices. So now you put 1. So you add extra digit, and the extra digit is going to be either 0 or 1. Well, if you put 0 in front, it's not going to change anything. So we'll put 1. And again, with that 1 as a first digit, please notice you could either have for second digit choice of 0 or choice of 1. So that's what they actually have for the next couple of numbers. So for second digit, it's either 0 or 1, when 1 is on the first place. So you had 2 numbers, and then when you have extra digit, you have 2 more numbers. So please notice that now they have doubled. So they have 4 new numbers produced with a digit 1 on the first position. So if they have extra position, and if they put 1 in it, wasn't careful. So if in the first position we have 1 here, here, and here, then the other 2 positions will exactly repeat what we used to have in here. So we have a, you can put just a couple of zeros, 0, 1. So 2 zeros, that's right there. Then 0, 1, right? And then 1, 0, and 1, 1. So you have next is 1, 0, and finally 1, 1. And this way you exhausted all possibilities for 3-digit numbers. So the next group will be 4-digit numbers, and please notice that now we have all the previous, which is 2, 2, and 4, which is total of 8. So this 8 will be again in here, but with an extra 1 attached in front, and so forth. So the next group should probably be twice 8, which is 16. So if you start to exhaust all the possibilities. Let's say if you're looking at the next one, what should be next one? 1, 0, 1, 0, 1, and that's going to be actual 21 here. So please notice that if I have like 100, 1 and 2 zeros, the next will be 101. But the extra one. And so forth. So the next, I cannot use 2, so put 1 and 0. So you can try to think about this over weekend if you feel like it. Point of story, it's unusual. It is unusual. So that's why I don't want to hurry with this. I just slightly touched this section 2 today, and we're going to spend more and more time with this base 2 numbers and the, I guess, class meetings next week. But now I'd like to return back to the previous section. So the homework will actually be for only this little group of exercises. So let me clear again this mess produced. So this group of exercises will be for homework for Monday. Again, it's not due in writing. You just do it on your own paper, the homework. And eventually, when the midterm day comes, you just send it to me by email, all of the homework together. Don't send me every time when you do homework, because it's going to be very difficult for me to keep track of what one done and what the other person didn't. So just collect all your homework little by little. Maybe a good idea to do it in some notebook in one place so you don't lose it. And then when the midterm exam comes, and that's going to be in 3 weeks, you just make copies of all that homework and email it to me at once. So we looked at some of these problems today. So how about if you try to do one of these little exercises for a quiz? So let's try, for example, let me do problem 3, and then you'll have analogous exercise to it for a quiz. So what I want to do is multiply a bunch of factors of 2. Oh, if you want to create some WhatsApp group or something, yeah, you can do that. That's, I guess, a great idea. So you can study together. That's helpful. So anyways, if you need to find what 2 cube equals to, what you do is you just multiply 2 with itself 3 times. And this is going to be 8. Well, I guess that's our old familiar way to multiply the numbers, right? So what I'd like you to do now is to produce the answer for exercise 4 as a little quiz. So how can you do that? Well, you should calculate on your own, say get a piece of paper and calculate what 4 to the power of 3 is. And it's going to be very similar exercise to what I just did with 2 cube. And then put your answer in the chat, just like you just tried to do this and creating this study group for this class. So put it in chat, but don't send it to everyone, because this way everybody will see what your answer is. And this is quiz, so it should be done personally. So you just send it only to my name. So please don't hurry. We have plenty of time. And calculate what 4 cube is, and just send this answer only to Alex, only to me. Don't send it to the whole class, because you might send this, if you calculate it incorrectly, the entire class will be very upset that you tricked them, right? So just send only to my name, And that'd be our quiz for today. And after you're done with the quiz, well, I guess you can log out and relax a little bit and start to enjoy the weekend.